logarithms, which is a section that, honestly, I don't know that we're going to do some recursive formulas, which I don't think you do in Math 3, but I think pretty much everything we do with logarithms is done in Math 3. Now, we have established that we come from varied Math 3 backgrounds. If you three that had Math 3 last semester, you're probably going to be at an advantage because you had real school and it's very recent. So that's probably going to be an advantage for you. Some of our Math 3 might have been over a year ago and online, so you may need more of a refresher. So those of you that just had it might be like thinking I'm going a little slow. Those of you that have not had it in a while, you might have some trouble. So just ask questions if you have anything. So a logarithm. Logarithms are really, really useful in the real world. Although I'm probably going to say this more than I would like to, we are not going to do a ton of application with logarithms. There's a couple reasons for that. Number one, in pre-calculus, we just have a lot to cover and not tons of time to go into in-depth applications. The other thing is the application of logarithms. There's lots of places they apply, but a lot of them I don't have the background knowledge to like really do something just this in-depth because they're in like more complicated scientific sort of situations. So we'll talk about them some a little bit. There's a few that are more accessible that we'll definitely look at, but logs show up in a lot of different aspects. A logarithm is the power to which a number must be raised in order to get some other number. Okay? So an example of when you're thinking about a logarithm is if I have 2 to the x power equals 16. What I'm doing there, and this should be one hopefully we can figure out 2 to what power would give us 16. Fourth, right? So I would say here that x equals 4. So the thought process you just went through there was actually taking a logarithm of that. You were saying, what power do I have to raise a 2 to that would give me 16? So what you're really doing there is you're doing the base is 2. This is the base. You're doing the base 2 logarithm of 16, and so it would be 4. And the way that we write that is log base 2 of 16. So when we see logarithms written, we're thinking the base raised to what power would give us this number. So another example that I've given here using, again, another one that we can figure out, although this one not quite as easily. 2 to what power gives us 1024? You can use your calculator here, see if you can figure out what that should be. Okay, so x would be 10 here because our base 2 logarithm of 1024 would give us 10 here. This is like the thought process you're going through here. But I gave you 2 here that were ones that were perfect numbers, right? So you could either, in the first one we could do in our head, the second one we might need the calculator to check for, but we could get an exact number. But we're going to run into ones where it might be like 7 to what power equals 8, right? We can't solve that in our heads or even using our calculator because unless we have some sort of mechanism for dealing with that, because we could guess and check all day, and we're not going to be able to come up with the number here. We know. 7 to the first power would be 7. We know 7 to the second power would be 49. So it's going to be like it's going to be like 1 point something, right? Probably like 1.1, but you're really going to have to just take forever to try to guess and check that. It wouldn't work. So we need a way of solving this, and that's where logarithms come in. Exponentials and logarithms are inverses of each other. They undo each other. Kind of like addition and subtraction are inverses, multiplication and division are inverses. So, let's talk a little bit about places where we use logarithms. A couple years ago when I was redoing these notes, I looked into this a little bit more. I found this really interesting. The Richter scale is logarithmic, but I found it interesting that the Richter scale is actually not used anymore. The one that they actually use now is the moment magnitude scale, but you pretty much always hear people still calling it the Richter scale. It's actually like a different formula that they use to calculate whatever. I wish I knew more, but I don't know exactly how those are different. But it's actually a different scale, but it's they're similar to each other. So Richter scale is what we think of, but it's actually the moment magnitude scale that you're going to hear reported when you have earthquakes. It is logarithmic with a base of 10. So you may have heard this before, but like if you have a Richter, if you have a earthquake that is a 5 versus an earthquake that is a 6, an earthquake that is a 6 is 10 times worse than an earthquake that is a 5. Because it's like 10 to the 5th power versus 10 to the 6th power, right? So it's 10 times worse. If you have a 7, it is 10 times worse than the 6, which means it's 100 times worse than the 5, right? 10 times 10. There. Another thing that operates the same way as the decibel scale for sound intensity. So whenever you're measuring the different sounds, and I'll show you a couple examples here in a second, is something that you're going to see there. Data analysis is somewhere you're going to see this, particularly when you have to deal with really, really large numbers. So really anything where you're dealing with really large numbers, logarithms come into play. So on the next slide, there is an example of the Richter scale. I just used this one. So we had, a couple years ago, we had that earthquake in Sparta. You could feel it. What was it? What was it? A 3? Yeah, it was like a 3, but you could feel it a little bit. So here it says it might be felt by many people, no damage, and it probably was like higher 3s, because I think there was, in Sparta, there was some slight damage of some like weak structures and things. So it fell right here. But if you had a 5, it becomes much more intense, where you got damage to weak structures. If you have a 6, moderate damage, but you go from a 6 to a 7, you're talking about serious damage, loss of life, right? So that sort of threshold between 6 and 7 is huge. And then if you talk about the difference between 7 and 8, severe destruction, loss of life, it's catastrophic, especially in places that are not built with like earthquake codes. Places like California are going to have building codes that are going to be able to take it a little bit more than if you're in Haiti or somewhere where they probably don't have any real building codes there. So it's kind of interesting to think about. One thing I've been thinking about a lot lately, and when you read statistics in the news, they drive me crazy. Because they put statistics everywhere, and a lot of times they don't give me the information that I really want to know. Like, child hospitalizations are up 50%. And then you want to say, how many were there at the beginning? Because if you go from 2 kids in the hospital to 3 kids in the hospital, that is a 50% increase. But it does not sound very alarming to me, right? But if you go from 200 to 300, that's an extra 100 kids. That's a little bit more alarming. Even though it's the same rate, there's a difference there. So sometimes they drive me crazy. They don't give me the information that I want to know. But we had original coronavirus, which shut us down, made us stay home for 3 months. It was crazy. Then comes Delta, and they say Delta's like, I don't even remember. I've heard like 7 or 8 times more transmissible, although I realize we're still learning things about it, and it's all over the place. So it's 7 or 8 times more transmissible than original corona. And then we got Omicron, which is, the scariest of all Greek alphabet letters, apparently. And it's supposed to be however much more, I've read like 10 times more transmissible, but I've also seen 2 or 3, I don't know. If it is 10, though. And Delta was 7 or 8 times. We're almost dealing with a logarithmic scale here, where that means that we are 80 times more transmissible than the original corona that they locked us in our house for. Which is either, to me, like, it doesn't even seem like it could be true, and maybe it's not, I don't know, they're still learning a lot of stuff about it, or we definitely shouldn't have locked ourselves in the house at the beginning, or we should be there now. I don't even know. I don't even know what to think about all of it. But it's interesting stuff to sort of think about, because that's sort of logarithmic scale. And whenever you're talking about coronavirus numbers, that's something that you can definitely think about, because you're talking about really large numbers of data. So logarithmic stuff comes into play there. Noise levels, here's another example. This I don't love. I like this chart, but here's what I don't like about this chart. It doesn't go up by standard numbers, 30, 40, 60, 70, 75, 80. I think it's just trying to pick very common ones, but I prefer if it went up by tens. But you can see to go from like 70 to 80. This is office noise inside your car at 60 miles per hour. Like, that's not very loud, right? But if you go to 80, heavy traffic, window air conditioner, noisy restaurant, power lawnmower, like, that's pretty loud. That's going to be something that, is going to give you trouble. But if you go from 80 to 90, now you're talking like subway, shouted conversation. You go 90, so this is about 100. This is school dance, which for me is always too loud, but I'm getting old fast, so that's the case. We used to have one teacher that would come to chaperone prom, and he brought earplugs. If you tried to ask him something, he'd have to take his earplug out while he was there. So you can sort of see, like, the different nature of this. It's 10 times louder each time. So I wonder if that's the case. I need to measure this. Whenever, like, on guitar amps and stuff, like, goes 1 to 10. I wonder if that's logarithmic or if it's not. It seems like it should be, because when my husband has it, he likes to play a lot of music, and when he has it, it gets, sometimes he'll turn it up just a little, and it seems like it's about to explode my eardrums sometimes. So that would be interesting to look into that. All right, so let's do some math. I've talked a lot about applications, but let's do some math. So logarithmic and exponential equations are inverses of each other. So if we have a expression that is written in exponential form, like b to the x equals a, then the logarithmic form of that is log base b of a, and you can use those parentheses or not. If you got an expression here that's got more than one thing you want to use them, but you can use them or not, would equal x. So there's a couple different ways you can think about doing this, and I'm going to show you both. So you can just think about this formula in rewriting. So whenever you're using a logarithm with something with exponents, you're generally doing that to break up whatever two things are right here beside of each other. So the 5 and the 2, you want to get them not beside of each other anymore. So whenever you rewrite this, whatever the base of the exponent is, because see here, this would be called the base of the exponent, it has to be the base of the logarithm, so it's the base in both places. So we're going to have log base 5, and then it's not going to be log base 5 of 2 because those two are together. We were wanting to split them up. So it's got to be log base 5 of 25. Is going to equal, the only other number we got left there is 2. Okay, the other way, I have been thinking about this lately, and I think I like this way better. But either one works perfectly fine. If you have 8 to the third equals 512. If we think of it like this, logs and exponentials are inverses of each other. So that means if I have log base 4 of 4, then those are going to cancel out and just equal 1. Alright, so if I have log base 4 of 4. So if I do this, if I do log base 8 of both sides of this equation, log base 8 of 8, that's going to cancel out, and over here you would just have 3, and then over here you would have log base 8 of 512. I've been going in that direction more lately. I think when you get to solving equations, it kind of makes more sense, but either one is fine. So like here, if I've got 6 to the x equals 125, if I think of my base here is 6, so if I think of doing log base 6 on both sides of this equation, the log base 6 and the 6 right here cancel out, just leaving the exponent, which is x. And then you would have log base 6 of 125 on the other side. Okay, questions? This program is possessed, and sometimes does crazy stuff. But all my notes are in here, so I have to keep using it, even though it probably should switch to something else. I can't redo all these notes. It'll take forever. So rewrite each logarithmic equation in exponential form. So this time we're starting with logs, we're going to exponential. So you can just go straight using the formula. So if I have the base of 5, it would be raised to the 4th power, and then it would equal 625. So your base of your logarithm has to be the base of the exponent. Raise it to the power of this over here, and it equals 625. Or, I kind of like doing it this way. If I have a log base 2, the inverse of that is to raise it to be a power of 2, like that, 2 to the log base 2. So I could do that on both sides of this equation. And the 2 to the log base 2 will cancel out the log. And you'll just have an 8. And on the other side, you'll have 2 to the third. So if I have here a log base 7, to get rid of a log base 7, I could do 7 to that power on both sides of this equation, which would cancel out my log and give me x equals, and over here I've just got 7 to the 10th. Okay, have you guys seen this before? Remember doing it? Okay, it's familiar. Okay. All right. So, some special logarithms to talk about, ones that are used really often. The common log, if you ever see log written without a base, it is assumed that that base is 10. So whenever you see log x, that is log base 10 of x. And then for natural log of x, that is a log base e. Are you guys familiar with e? Some of you not. Okay, e, if you type it into your calculator, e is called Euler's constant. Euler, though, starts with a E, E-U-L-E-R. It's one of those words that if you didn't hear anybody else say it, you would not call it Euler. But if you hit second and the division key on your calculator, it will bring up an E. If you hit enter, it will give you the decimal approximation. So it's 2.718281828. It looks like it's a repeating decimal, but it's not there. It's irrational, like pi. So this would just keep on going forever. It's very similar to pi. It's Euler's constant. It is one that we have established. Math is just so cool and so crazy. Like it shows up in all kinds of places where it really doesn't even seem like it should show up in math. So it applies in like a lot of different situations. What we find is it models like natural phenomenon really well. So if you're looking at like exponential growth of maybe bacteria or exponential growth of populations or something, the E, you guys have probably seen the formula, the PE to the RT for exponential growth, hopefully, and we'll look at it some in here if you haven't. It uses this value. I will try to do a warm-up either tomorrow or next week on where it comes from and, a little bit more about it. Or actually, there might be a video we might watch because there's a really good video that I think I showed everybody last year from some of my favorite math YouTubers there. So we'll talk a little bit more about it. But E is a lot like pi. It is a number. It's always 2.718 there. And so you're going to see this used a lot. In fact, in calculus, we pretty much only use natural logs whenever we're dealing with logs. Very rarely you'll see logs, just common logs used, and hardly ever will you see a different base. But we'll deal with a little bit of all of it here. So these are two that you'll see. Okay, so logarithmic and exponential functions are inverses of each other. We've kind of already done this, but that means that if f of x equals log of x, do you guys remember finding inverse functions in Math 3? Anybody remember how to find an inverse function? You switch the x and y, and you solve for the new y. So that would look like this here. That f of x here, it's like our y. So we would have x equals log of y. And then this doesn't have it written, but it's a 10 right there. So if I want to get rid of the log base 10, I could do 10 to that power on each side. That would get rid of my log. So I would have 10 to the x would equal y, or I could, instead of calling it y, I could call it f inverse of x equals 10 to the x. So they are inverses of each other. It's much like if you have x plus 2, the inverse of that would be x minus 2, right? In a more simple one. So if you did the same thing over here, if you took this and made it x equals 10 to the y, in this case, to get rid of that exponent as a 10, you can't divide that 10 off. You've got to do log base 10 on both sides, and so log base 10 of x would be your y, or you could write it like this, g inverse of x equals log base 10 of x. So we'll use that pretty often. A couple other things that we need to know before we start solving equations. The domain of a log. You cannot take the log of any number that is less than or equal to 0. So let's think about why that is for a second so that makes sense to you, because this is something that often we forget to check for. Let's say I'm trying to do log, it doesn't matter what the base is, I'm going to do log base 3 of negative 2. And I don't know what that equals there. So to get rid of a log base 3, we need to do the inverse, which means we need to make it the power of an exponent here. So we do 3 to this power here to cancel out that log, meaning we do 3 to the question mark here. So that gives me negative 2 equals 3 to what power? So think about raising 3 to a power. Is there any power you can raise a 3 to that's going to give you a negative? It seems like maybe a negative power should work. But if I do something like 3 to the negative 2, anybody remember what to do with negative exponents? Yep. So it's on top of the fraction bar right now. We'll move it to the bottom, and we move it to the bottom. We make its exponent positive. So that would actually be 1/9. Right? So like if you put a negative exponent, it's just going to give you a really, really small fraction, but it won't give you a negative number. So there's nothing that will work here. So you cannot take the log of any number that's negative or 0, because if the same thing is true, there's no way we could ever get that to equal 0 either. So if you find yourself having to do log of a negative number or log of 0, then it's probably no solution for that problem. Or you've messed up earlier and shouldn't be doing that anyway. Okay, one last thing before we get to solving equations is your change of base formula. Depending on what calculator you have, you may or may not need this. My calculators are really mixed up. I had the very, very oldest set of calculators, but lots of them have died, so we've bought new ones to replace my dead ones. So some of my calculators in this room are some of the newer ones. Some of them are super old, and there's a little bit different operating system on them. Some of you guys have the newest ones that you plug in to charge, and I think they should do these logs where you don't have to do change of base, but it's still just good to know. So if I'm trying to do something like log base 5 of 7, right? If you have the older calculators, without going to math and going through a bunch of menus and all kinds of stuff, there's no way to do it. But what you can do is you can use the change of base formula, which would be, I really don't like the way I did that. I'm going to change this. I do not like using the letter B as, I like B as the base. Let me fix this. If this bothers you, you can change it for yours too. But let's, I like B to be the base of the log there. If that doesn't bother you, it's fine. It's correct the way it is. I just don't like B not being the base. So it's going to be log of the big number, 7, over log of the base. It actually can also be, you can use natural log of 7 over a natural log of 5. It doesn't matter. Both are going to give you the same answer. So it just makes it a lot quicker to type into the calculator if you don't have the new ones that let you change the base. So log 7 over log 5 will give you this value. You could also use natural log. Just make sure you close your parentheses here. If you don't close that parentheses, it won't give you the right answer. Natural log of 5. You can see you get the same even if you use natural log instead of log. There's also a chance that there might be questions maybe like on the ACT or something where they're wanting to know if you know the change of base formula. So the answer choices might look like log 7 over log 5. Can't guarantee that would happen, but it's possible. So you might need to know it for things like that. If you use Desmos at home, for Desmos, when you type this in, you can go to functions, miscellaneous. There's an option where you can change the base, so log base 5 of 7, and it'll just give you the value. Or I still don't even use this with Desmos because I like to be able to type it in without having to go to the menu, so I just do log 7 over log 5. Still, you get the same number, so it's up to you on this and that. Alright, so let's solve some problems here. So if we have exponentials, so these first 4 that we have here are exponentials. Whenever we want to solve this, the biggest mistake I see students making is that they try to do like this. They divide both sides by 5. You cannot divide both sides by 5 because this is not 5 times x. It is 5 to the x power, which is different, right? The opposite of multiplication is division, but the opposite of raising something to a power is a log. So I just like to think of it like this. Log base 5 on this side will cancel your base. The exponent is still there. And then I'm also doing log base 5 on this side. So I got x equals log base 5 of 9 in the end. That we can just type into the calculator real quick here. Log 9 over log 5 is going to give us 1.365. As a general rule of thumb, if I have not told you otherwise, keep at least 3 decimal places on your answer. If you take AP Calculus on the AP Calculus exam, all the answers have to be rounded well, they don't have to be rounded to 3 decimal places. They have to be correct to 3 decimal places. So that is generally what I do, unless there's like some other reason it'd be better to round to something else. For logs, there's pretty much not a reason to round it to something else. So your final answer, keep me at least 3 decimal places. What I will do is the way AP does it as well, most of the time, is if you give me more decimal places, that's fine. So if you give me 1.36521238.9, that's okay, but make sure it's correct up to at least 3. Don't round it off more than that, unless I've told you otherwise. So let's look at number 2. So Maddox, what would we do for number 2? Very good. All right, and what will happen on that left-hand side? Very good. And over here, we've just got log base 8 of 450. And what do you get whenever you do that, Max? How would we type that in? Other way around. The big number goes on top. Log 450 over log 8. Sometimes it's hard to remember that, but I always think that the base has to be on the bottom. So we get 2.934 or 938 if we round to 3 places there, or keep more, that's fine. Okay. For number 3, it's a little bit more complicated. We've got 10 to the power of 2x minus 4 equals 800. So for this one, we're trying to get that x by itself. The first thing we've got to get rid of is that 10 that's your base. So Blaine, what would we do to get rid of that 10? Good. So we'll do log base 10, which is actually just your natural log, or not natural log, common log. So you can write the 10 if you want, but you don't have to. And so that'll cancel over here. We get 2x minus 4 equals log of 800. And log of 800 is going to be a number. So we can just type that into our calculator. Now, don't round here until you get completely finished with the problem. It's fine if you round what you're writing down, but keep that number in your calculator. Okay, Blaine, what would we do after that? We're trying to get that x by itself there. Perfect. We'll add 4 first, and then we'll get 6.90308, and then last step, Blaine. Just divide by that 2. Very good. So, if I add 4 here so I don't have to. And then we get 3.452. Okay, questions? All right, for number 4, this time we need to get rid of that 10, but the 10's not the base. Grace, what would we do first to get rid of that 10? Okay, imagine that you had something like 10 minus x equals negative 9. What would you do there to get rid of the 10? So if it's a positive 10 right here, how would we get rid of it? We just subtract it, right? It's the same thing here, because all of this stuff we're going to deal with separately later. It's separated out by minus sign, so don't worry about the crazy stuff behind it. If you want to get rid of this 10, you just need to subtract it. And so now we're going to have negative e to the x power equals negative 19. I got that negative that's messing me up. How do I get rid of that negative? Just divide by a negative 1 there. And so you'll have positive e to the x equals positive 19. Now I'm getting to the point where I've got to worry about logarithms, right? So you want to get that exponential expression by itself first before you try to do any logarithms. You wouldn't do those first. So I've got e to the x power, so that means I need to do a log base e. What's the, what do I call log base e? It's got a special name. Natural log. So I natural log both sides. So x equals natural log of 19. And so we can type that into our calculator. And 2.944. for right now, that's about as complicated as we're going to get on solving the exponentials. Let's look at somewhere we've got log equations. Okay, for number 5, I've got log x equals 90. This one does not have a base written, so what is the base? 10. All right, so there's an invisible 10 here for our base. So to get rid of a log with a base of 10, we are going to take 10 and raise it to that power. And that cancels out your log with its base, but not whatever you're taking the log of. So we've got an x left on this side. And then over here, we have 10 to the 90th power. And that would be a 1 with 90 zeros. So we're just going to leave it 10 to the 90th power. If you find yourself, sometimes with logarithms, I try to make them where, like for just worksheets, I try to make them where you're not getting crazy big numbers. But sometimes I don't do a very good job of that. So if you get something where you're getting crazy big numbers, it's okay. Like if the calculator gives you scientific notation, to leave it scientific notation, or just leave it with your exponent instead of trying to write out 90 zeros there. So, let's go on to number 6. Okay, we've got log base 5 of x minus 4 equals 20. So, Noelle, what would we do to get rid of this log base 5 right here? We'll make it to the power, 5 to that power. I tell you what, I was doing a terrible job on these notes here. For the sake of not having to have a gigantic number again, mark out that 0 and let's just make it 2. Because otherwise, we're going to get a giant number that I don't want to deal with. So, that's just because I didn't make the best practice problems here. So 5 and log base 5 cancel out. We're just left with x minus 4 over here. 5 to the second would be 25. And then, Noelle, what's the last thing you would do to get that x by itself? Perfect. So x is going to equal 29 for that one. Okay. 7, I've got all kinds of things over here. I got this natural log of x right here. But I got other stuff outside of that natural log of x. So I need to get rid of those things first before I try to deal with that natural log of x. Jackson, what would we do first here to try to isolate that natural log of x? Very, very good. So we got 2 natural log of x equals 4. What would we do after that, Jackson? Perfect. Very good. Now we're down to the natural log. Jackson, what do we do to get rid of a natural log? What's the base of a natural log? Let's say that word. It is an e. So it doesn't have it written, but there's an e to the base. So we're going to do e to that power there to cancel it out. So x would be e to the second power, and e squared, if we get a decimal approximation for it, is going to be 7.389. Okay, questions? All right, got one more, and then hopefully you'll have some time for your assignment today. So we got log of 4x minus 3 equals log of 3x plus 10. So here we need to get rid of the logarithms. They both have the same base. If you ever get one that does not have the same base, I probably have messed up on the problem because they would be really, really hard to deal with. So these have a base of 10. So if we do 10 to that power on both sides, it's going to cancel both of the logs out, right? So because everything's on the inside of those logarithms, we can just raise both sides to that 10th power to make both sides that power of 10, and you're just going to have 4x minus 3 equals 3x plus 10. Coach Wood really likes to talk about dropping the logs here. He finds that phrase pretty humorous, and if he were to walk by right now, he would probably stick his head in the door and say something about dropping logs. So if you have everything is inside of a logarithm on both sides, you can just drop those logarithms and just set the two equal to each other. So now you're at a basic equation. You're just going to subtract that 3x. So x minus 3 equals 10. We could add that 3. So x is going to equal 13. Okay, questions? Okay, we just need a lot of practice with it, I think, is probably a good idea, because these are pretty quick to solve. You just need to do a lot of them to make sure you've got it down. So I have a lot of them on your assignment tonight. You will not normally have 39 questions. I think it might actually be more than 39, because I want to say I numbered one of them twice, maybe. You will not normally have this many, but I don't think it will take you a terribly long time to do this. And I'll be around to help if you have any questions. Everybody's panicking. Everybody's good. Drop it immediately. Right. Got it together, okay. Alright, so this will be your assignment for tonight. Go ahead and work on it now. You might be able to get it done before you go. Also, especially here at the beginning, now, towards the end of last semester, I quit doing this as much because I started not to trust some of my students not to just copy it down. But especially here at the beginning, I know you want to check to see how you're doing. So here, if we have a worksheet, I will probably post the answer key I have for this one. So the answer key is up on Canvas if you click on that assignment. So whenever you finish, you can check your work to see if it is correct there. So please do check it tonight before class starts tomorrow, because I'm not going to call out the answers for that.